Hello again, everybody. Back for the last problem on this even more nuclear reactions practice worksheet. We're on to the Back to the Future problem. It requires 1.21 gigawatts, or pronounced gigawatts, to power the flux capacitor used in the DeLorean in the movie Back to the Future. If that power was needed to travel 25 years into the future, and a watt is a joule per second, how many joules were required to power the flux capacitor? So this is really just a train track problem. No nuclear stuff going on in part A. We're going 25 years into the future, and we see that our unit for the watt is in per second. So if we want to use this joule per second as a conversion factor, we need to get our time into seconds. So every 1 year is 365 days. Every day is 24 hours. Every hour is 60 minutes. And every minute is 60 seconds. From there, we can use our conversion factor with watts, that there are 1.21 times 10 to the 9th joules every second being used by this flux capacitor, or 1.21 times 10 to the 9th watts, a watt being a joule per second. So 1.21 times 10 to the 9th joules per second. That is going to leave joules as our only unit uncancelled out. And you get rounded to, I went with 3 significant figures because of the 1.21, 9.54 times 10 to the 17th joules. I would not use the 25 years as a significant figure. It's just a number of years. It's not a measurement, whereas the 1.21 is. Part B, plutonium is a radioactive element, so on and so forth. Don't let yourself get bogged down in the part above. It says what mass in pounds of plutonium will be needed to power the time machine to travel into the future. We already know from part A how much energy we need. We need 9.54 times 10 to the 17th joules. That's going to carry over into part B. We want to know how many pounds of plutonium we need to get that much energy. It tells us in the problem that plutonium decays by alpha emission. Start there. Plutonium symbol is Pu. It's got 94 protons. And we're talking about plutonium-239, so that's the mass number. Alpha emission means you're getting rid of an alpha particle. And your other mass is going to have to be a mass number of 235, atomic number of 92, and that's uranium. Now that we have our reaction written, we can look and find the mass defect. So if you add up the mass of your reactants and your products and find the difference, that's going to be the mass defect. Plutonium's mass is given as 239.0521634 AMUs. The mass of helium plus uranium together is going to be 239.04407 AMUs. We see the mass gets lost a little bit. That's because it turns into energy. We can find the difference there by subtracting. Our mass defect is going to be 0.00809 AMUs. That's our mass defect. From here, we can find out energy per atom of plutonium, how much energy we're going to get per atom. So E equals mc squared. Our mass here is 0.00809 AMUs. Conversion factor 1.6605 times 10 to the minus 27th kilograms per AMU, multiplied by the speed of light squared. And you get an energy right here at the bottom, 1.209 times 10 to the negative 12th, and that would be joules per atom of plutonium. Now, we haven't quite finished the problem yet. We know how much energy we would need total based on answer A, and we know how much energy we get per atom of plutonium based on what we've gotten so far. So now we can figure out how many pounds of this plutonium we're going to actually need. So I'm going to take the number of joules we got in part A, 9.54 times 10 to the 17th joules needed. And we're going to train track this thing until we get to pounds of plutonium. The number we just came up with, I'm going to put that in the denominator, 1.20901 times 10 to the minus 12 joules for every 1 atom of plutonium. For every mole of atoms of plutonium, you get 1 mole of plutonium. Keep this going over here. And every mole of plutonium has a mass of 239.0521634 grams. And I gave you the conversion of kilograms to pounds, so we need to get this to kilograms first. 1,000 grams for 1 kilogram. And every kilogram is 2.2 pounds. This is of plutonium. So our only unit that hasn't canceled out is pounds of plutonium. I'm going to round it to 3 significant figures because of our 9.54 number we started with. And I'm going to get, 3 significant figures. 689,000 pounds of plutonium, which is an insanely large number. Don't think that that's a realistic number. I don't think the people who were writing the script for Back to the Future really did all of the mass defect calculations to see if this amount of mass would fit inside of a DeLorean. I think they just wrote a funny word, and they liked the word gigawatts. Finally, part C. It says if the density of plutonium is 19.84 grams per cubic centimeter, what length in millimeters would this cylindrical pellet need to be if the radius of the pellet is really small, 1.66 times 10 to the 8th nanometers. So we know that these pellets are cylindrical in shape. We want to know how long they are. And we're given the radius. Now you got units all over the place here. We've got grams per centimeter cubed, we've got nanometers, we've got millimeters. We need to have some sort of consistency here. So first of all, I'm going to take this mass that we got for part B, and I'm going to use the density to turn it into a volume, because we know the volume of a cylinder is going to be pi r squared times the height, or the length, whichever way you want to say it. So I can find the volume using the density in our answer from part B. So let's start there. We've got 689,000 pounds of plutonium. I'm going to go from pounds to kilograms because I know there's 2.2 pounds per kilogram. I know for every kilogram there's 1,000 grams. Now I can use the density. There's 19.84 grams of plutonium per cubic centimeter of plutonium. And since I want my answer at the end of this problem in millimeters, I'm going to go to cubic millimeters. I know that every centimeter is 10 millimeters. Now, if I only did that once, I would still have centimeters squared in the numerator. I want to get rid of that, so I'm going to actually do this step 3 times. By doing so, I can cancel all the way out to millimeters cubed to get the volume of this fuel pellet. Rounded to 3 significant figures is 1.58 times 10 to the 10th cubic millimeters. That's our volume. Now, in order to use my volume of a cylinder equation, I need to have everything in the same units. So millimeters is the way I'm going to go. I've got the volume in the correct units. I'm looking for the height. I need the radius in the correct units. So I'm going to take the radius, 1.66 times 10 to the 8th nanometers, and try and change this into millimeters just so they're all in the same unit. I know that 1 nanometer, there are 1 times 10 to the 9th nanometers in a regular old meter. And I know that a meter has 1,000 millimeters. Nanometers cancels out. So I end up with 166 millimeters. That's my radius of the pellet. Now I can use the volume of a cylinder equation, pi r squared times h, or the length. 1.58 times 10 to the 10th millimeters cubed is my volume. Pi, 166 millimeters is my radius, squared times h. So I divide by pi, divide by 166 twice, come out with a height of 1.83 times 10 to the 5th millimeters. As with the other problem, this is not a very reasonable answer. It's 183 meters long, so it's a pretty giant pellet. But that's how we solve. If you're studying, make sure you're looking back at all this previous stuff. And this problem by itself included everything from density, which was like a Unit 1 problem, all the way up through the nuclear stuff that we're in now. So anything is fair game. Good luck studying, and I'll see you guys on Tuesday.